Today I will present our work CAT. Localization and Identification Cascade Detection Transformer for Open World Object Detection. Firstly, what is Open World Object Detection? Here, the task is to learn to detect unknown object instances and incrementally learn to classify them into their respective classes. For example, the input image contains both labeled foreground objects like person and unlabeled objects like tennis racket and sport ball. The aim of the model is to detect novel unseen objects and classify them as unknown along with learning labeled instances. When annotations of these unknown labels are introduced, the open world detector should be able to categorize them accordingly without forgetting the labeled instances, and these steps continue until all objects are labeled. There are currently two main efforts that have begun to investigate open world object detection. But there are still many problems. The recent work ORE and OWDTR don't consider that the inclusion of detecting unknown objects substantially reduces the model's ability to detect known ones. Both of them guide themselves to learn unknown objects, without adequately utilizing the priori knowledge of inputs. In addition, fixed pseudolabel selection mechanism cannot guarantee that the model learns in the right direction, and so the model may become worse and worse for detecting unknown objects. In real life, when facing a new scene, people subconsciously prefer to focus on all foreground objects and then identify each one in detail, rather than localize and identify a single object simultaneously. Motivated by the front findings, we do the following works. We propose a novel localization and identification cascade detection transformer, CAT, in a cascade decoupled decoding way, which decouples the decoding procedure via the shared decoder. We introduce a novel pseudo-labeling mechanism that self-adaptively combines the model-driven and input-driven pseudo-labeling to generate robust pseudo-labels and exploring knowledge beyond known objects. And then we achieve state-of-the-art performance on two benchmark datasets. Our CAT model is a fully end-to-end framework, consisting of the multi-scale features extractor, the shared decoder in the cascade decoding and the self-adaptive pseudo-labeling mechanism. CAT utilizes the shared transformer decoder to decouple the localization and identification process for alleviating the influence of detecting unknown objects on the detection of known objects. In the cascade decoupled decoding structure, the location embeddings are used as class queries for knowledge retention. A novel self-adaptive pseudo-labeling mechanism is proposed for self-adaptively combining model-driven and input-driven pseudo-labeling according to the situation faced by the model. With the self-adaptive pseudo-labeling mechanism, CAT particularly maintains the ability to explore the knowledge beyond the known objects, and self-adaptively adjust the pseudo-label generation to the actual situation during the model training process. In this paper, the attention-driven pseudo-labeling is used as the model-driven pseudo-labeling, and selective search is selected as the input-driven pseudo-labeling. The flow of the algorithm is shown. For quantitative evaluation comparison, we employ URICAL for measuring capability in unknown setting and employ MAP for evaluating the known. As we can see, in comparison to other methods, we achieve state-of-the-art results with absolute gains. Visualization results comparison between CAT and ground truth. As shown in the figure, our model can accurately detect known objects and unknown objects outside the total class of the dataset, such as the electric plug and sound switch in the first column, the camera in the second column and the kitten toy in the third column. It is also worth noting that although our model detects the audio, it does not identify it as an unknown object, but as a remote, showing the limitations of our model. Visualization results comparison between OWDTR and our CAT. We use OWDTR and CAT, which are both trained on task 1, the known classes are VOC classes. OWDTR cannot detect real unknown objects that are not in class 80 of the COCO dataset, but our model CAT can accurately localize and identify almost all known and unknown objects. The results show that our CAT substantially outperforms OWDTR in terms of the ability to explore unknown objects and the detection accuracy. Visualization results comparison on incremental object detection. We visualize the detection results of the weights corresponding to different tasks for the same scenario. The results show that our cat can identify unknown kinds of objects as the unknown class and accurately identify their classes after incrementally learning the unknown classes, such as sports ball and tennis racket in the first column, surfboard in the second column, and traffic light in the third column. That's all our presentation. Thank you for your listening.